So let's start. Hello, everyone. Thank you for joining today. Welcome to our webinar, Advanced Techniques for Reducing Eddy Current Losses in Magnets. I'm Frédéric Perret, Head of Marketing at PowerSys, and I will be your host. Our today presentation will be presented by Stefan Paul. Hello, Stefan.
Hello.
And Bernd Cybulski will be also attending the session with us, supporting us for the question and answer during all this session. And if you have also additional questions, both of them will be able to answer. Stefan finished his studies in electrotechnics with a focus on power electronics and electric drives in 2009. From 2009 to 2023, he worked at IAV with a focus on electromagnetic design of electrical machines, test of electrical machines, simulation and test of inverters and rotor position sensors, requirement engineering. In 2023, Stefan joined PowerSys as a technical account manager, and since then, he helps customers to design their electric motors. Over the next hour, Stefan will explain how advanced simulation methodologies, including magnet segmentation, 2D and 3D modeling, and optimization of mesh quality and time state parameters, can reduce eddy current losses and enhance the efficiency of electromagnetic systems. Before we get started, there are just a couple of things I want to tell you so you can get the most out of this webinar. Stefan, Bert, and I are happy to answer questions as we go along, as I mentioned. Just feel free to post them in the Q&A box at the bottom of your screen. There will be also a time for a Q&A at the end of the session if we have not been able to answer all the questions during the webinar via, again, the Q&A box. During the webinar, we will also conduct a series of quick polls to gather your immediate feedback. So please don't hesitate to participate. Your input is invaluable to us. Lastly, if you can take some time at the end, we will be really grateful if you fill out our 5th question survey. Again, these surveys are also a way for us to improve our webinars in the future. First, let me start with a quick introduction of PowerSys for the people who join and who don't know PowerSys. So at PowerSys, we are expert in electrification since 2002. Our mission is to move e-motor design to zero prototype. Our solutions enable OEMs to minimize hardware prototyping, decrease development time, increase precision for e-motor design. As a consequence, our clients are able to decrease their time to market and to increase their profitability. Our strategic focus is the acceleration of the electrical design in electromagnetics and power electronics, as you can see on this slide. And as you will see in our today's presentation, our solution for the electrical design in electromagnetics relies on JMAG, an electromagnetic massive simulation platform. Thanks to JMAG and our electrification expertise, we can deliver fully customizable model-based design platform to our customers. In addition of our today's session, I also would like to share with you, after this short presentation of our company, some upcoming events we will have. So let me show you first a webinar that will happen on October 4th, creating efficiency map analysis of axial flux motors using JMAG Designer. This webinar will be presented by our colleagues Supriya Singh and Kirtanasi. You have also the time frame, so 3 p.m. Indian time, I would say, and 11:30 a.m. our time in Europe. We also have a big event coming in Germany, our conference, Advanced E-Motor Design with JMAG. So during this event, we will demonstrate through different presentation of our clients how massive simulation help in accelerating innovation. This conference is structured over 2 days. On October 22nd, we organize 2 trainings in parallel, a basic one or advanced one. So depending on our level of expertise about GEMAG, you have the possibility to choose. And on October 23rd, we have our conference where we will have some featured speakers, and you can see them on these slides. So the keynote will be done by Alexander Rosen. Aline Stirban from Bosch will present as well. Carsten Müller from Mercedes, Matthias Lindler from IAV, Stefan Skug working at Alvier we also present, and finally Robert Holhaus from Hexagon will do again also in presentation. This event, as I mentioned, will happen in Germany in the Hotel Le Méridien in Stuttgart. So I will just post the links of these events in the chat box so that you can have them if you want to register. Without further ado, now I give the floor to Stefan. Stefan.
Thank you, Frederic. Okay. Today I want to discuss the optimization and electromagnetic design and the advanced techniques for simulating eddy current losses in magnets. So originally we have called or we named the presentation advanced techniques for reducing eddy current losses in magnets, but I think it was a bit too far maybe for us. Because the reduction of eddy current loss in magnets is a bit more the task of the e-motor designers, which will be you in the end. And for me, I would more like to focus on the how to simulate the eddy current losses in magnets, right? So the reduction of eddy current loss depends on, there are several techniques and measures to reduce eddy current loss in magnets. But e-motor design does not only focus on the eddy current losses in magnets. So the e-motor designer has to consider many other characteristics of the e-motor design, like performance, all-over efficiency, NVH, cost. And so this is basically not my task. So, but I want to give you the tools and the procedures how you can do this design work in the best way. And and that's why I renamed this presentation a bit to advanced techniques for simulating eddy current losses in magnets. And this presentation provides a comparison of the simulation results of 2D simulation and 3D simulation, and a comparison between sinusoidal current supply and PWM current supply. And at the end, I want to give a short advice and recommendations regarding mesh quality and how to choose time step for the transient simulation. Now let's start first with the motivation. So if you think about eddy current loss in magnets, I think the most important issues we deal with is at first the efficiency, the all-over efficiency of the e-motor, because it's losses, it's a loss component we have to consider in the e-motor. But I think the efficiency of the e-motor is not the most important issue regarding eddy current loss in magnets, because compared to the winding loss and compared to the lamination loss in the stator lamination, this is eddy current loss in magnets is a quite small component of losses. But if you focus a bit more on the rotor side, there, for PMSM, the major loss components are inside the rotor lamination and inside the magnets. And that's why let's say the eddy losses on the rotor side are really important for the total loss on the rotor side. And that is also why these losses are very important for the cooling concept of the rotor, which we have to implement, because mostly at high speed, at high rotational speed, the eddy current loss in magnets can limit the continuous performance. And this is because if the eddy current loss in the magnets increase, or if they are quite high, then also the temperature of the magnet rises quite strongly. And at some point, this temperature is too hot and could damage the magnet. So that's why in the end, you have to limit the output power of the e-motor to save the magnets from being damaged. And that's also the third issue. So we want to avoid the demagnetization of the magnets. And the idea behind is during design phase, we need to evaluate or to simulate very accurately the temperature of the magnets that can occur during operation to save the magnets from being demagnetized in some operating points or in some circumstances, like if we switch to active short circuit in a drivetrain of a vehicle, then this might cause some irreversible demagnetization in the magnets. And this strongly depends on the temperature. So if such active short circuit is far from being critical at, let's say, a magnet temperature of 120 degrees Celsius, it's very critical maybe at 150 degrees Celsius. And that's why we really need to accurately simulate these losses and also need to simulate accurately the thermal behavior of the e-motor to save the magnets from being damaged. Now, what could be the sources of eddy currents in magnets? So if you think about the fundamental model, LD-LQ model of the PMSM, there's only a constant flux and constant component on the rotor side. But in a real e-motor, we have to deal with several harmonic flux components. So, and these flux components lead to induce some very small voltage in the magnets, and this voltage drives an eddy current. And this is basically represented with the Faraday's law, and with this, one could calculate also analytically the eddy currents in the magnet. And this is basically the effect why eddy currents occur in the magnets. And sources of the flux harmonics can be, for example, the slot harmonics or the winding harmonics. So it can be influenced by the design of the e-motor. But there can also be some harmonics in the phase current, for example, due to PWM, or because we have a voltage-driven supply, like fundamental voltage supply, or if we consider a current control, which is not always able to impose a fully sinusoidal current into the motor. So then there will also occur some harmonics in the current, and all these harmonics in the phase current will induce flux harmonics and afterwards also induce additional eddy current loss in the magnet. And now here are some only very rough ideas how we could reduce these harmonics which excite the eddy currents in the magnet. So, for example, to reduce the slot harmonics, we could use closed slots, or we could also reduce the size of the slots and on the other hand side, increase the number of slots. To reduce the winding harmonics, we can also increase the number of slots, and to deal a bit with short pitching. A third method with the shielding, it's just for completeness. So shielding is a bit, let's say, complex because it can reduce the eddy current loss in the magnet itself. But then we have the, let's say, additional eddy currents in the shielding, and then magnets might be warmed from the shielding itself. So could be a solution or an improvement in the design, but must be considered by the e-motor designer afterwards. On the other hand side, we can also deal with the materials we use inside the or use for the magnets. So to reduce eddy currents, one can increase the resistivity of the material. So for example, we could, instead of sintered magnets, we could use bonded magnets. So the electrical conductivity of bonded magnets is very low, and so the eddy current loss of these magnets will be very low. The drawback is that these materials, that the poor performance of these materials is far lower compared to the sintered materials. Let's say some way in between is to use the segmentation of magnets. So with the segmentation, we do also somehow increase the resistivity of the magnets, but on a, let's say, in a larger dimension than if we use bonded magnets. And the segmentation of magnets I want to discuss on the next slides. If you want to consider segmentation, there are two ways usually that we can use. So this is on the one hand side the laser pointer. So on the one hand side, there's the axial segmentation. So instead of one big magnet, we divide this magnet into two parts in the axial direction. And we can also deal with the circumferential segmentation. This is a V-shaped rotor, so circumferential might be not exactly the right term for this, but a segmentation in the, let's say, 2D plane of the e-motor. So, and this could also reduce eddy current loss in the magnet. Here on the lower side, we can see an exemplary eddy current distribution for this example. And as you can see, it's a real eddy current which is flowing inside the magnets. And it's not only a 2D effect, so to really consider the this eddy current in the magnet, it's in an optimum way or in a perfect simulation, it would always consider a 3D simulation to account for the eddy currents. How can we consider how can we calculate the eddy current loss in the magnets accurately? I want to discuss, let's say, 4 approaches. Let's say the fourth approach is a bit trivial, but for me it's the reference in the end. So it's the 3D simulation. So compared to the 2D variants, it's quite slow, but provides accurate results because it can really represent the current path in the magnet and can really represent the loss distribution in the magnet accurately. And the first 3 approaches I want to discuss now a bit. So the first approach is the 2D simulation without any segmentation factor considered. Segmentation factor, I use this term always because that's, let's say, the segmentation factor is, let's say, the basis for the calculation. But here in this case, in this example, I use the approach of the segmentation factor calculation to recalculate the results from a 2D simulation to a 3D simulation. I will explain it afterwards a bit more into detail. So yeah, I just want to mention that segmentation always means in this exemplary case the recalculation of the results from a 2D simulation to a 3D simulation, or compared to a 3D value afterwards. And if we have a short look to the schematic of a 2D simulation, the blue area should represent the magnet in a 2D simulation, and in the orange arrows represent the current density inside the magnet, so the eddy current simulated. So one can see that in a 2D simulation, we can only consider the axial component of the eddy current, and we cannot consider the, let's say, the real eddy, the 3D eddy current in a 2D simulation. So because in a 2D simulation, the current density in X and Y direction will always be 0. And we can only consider the Z component of the current density in a 2D simulation. And this also means this eddy current will always be, or will not be limited by this resistivity in the X and Y direction. And this is something the 3D simulation can do. So because the 3D simulation can really represent the eddy current path inside the magnet. So it represents the axial direction, but it can also represent the X and Y direction inside the magnet. And this way, the eddy current in the magnet faces the real resistivity which it would also face in a real machine. And that's why there are several publications where analytical segmentation factors are calculated, or how the processes are described, how we can calculate these kind of segmentation factor. As said, I want to use these approaches to recalculate the results of a 2D simulation to a real 3D loss value afterwards. So, and this segmentation factor can be applied to the losses we have simulated with a 2D simulation. This is a quite convenient approach because in the first step, I can do the 2D simulation and calculate the losses with my 2D simulation. And afterwards, I can apply different segmentation factors. I can vary these factors. I can vary the segmentation of the magnets after my FEA simulation is finished. And so this way I could optimize the segmentation without doing new additional FEA simulations. There's one drawback in this approach, because this eddy current is not only limited by the, let's say, ohmic component of by the resistivity of the material, but for high frequency components of this eddy current, it is also the current is limited by an inductive component. So so the eddy current flowing in the magnet is not only limited by ohmic resistance, but also by inductive resistance or reactance. And this is overcome a bit with the third approach, because in the third approach, we do not apply this segmentation factor to the losses after the FEA simulation, but we feed this segmentation factor into the simulation before we start the simulation, and we apply this to the, let's say, resistivity or conductivity of the magnet material. So we reduce the conductivity of the magnet material using the segmentation factor. And this way we consider, let's say, the ohmic, the change of the ohmic component for the losses, but the inductive component remains as it is. And this way, especially for high frequency losses, we expect that approach 3 will provide more accurate results for a 2D simulation than approach 2 or approach 1. Yeah, and fourth approach, as discussed, is the 3D simulation, which we want to take as a reference. Now let's come to the model I want to use for this exemplary simulation. It's basically an internal permanent magnet machine with a V-shaped magnet, a quite simple rotor design without any notches on the rotor surface or any holes in the rotor to reduce inertia, for example. It's because this shall just be an exemplary use case for the e-motor itself. So it's a machine with 4 pole pairs and 48 slots. So this is a very typical e-motor variant for traction e-motors. The winding is made of an FEM coil. So this is a, let's say, a specific term used in the JMAC, used inside JMAC. So this means inside the winding, we cannot represent any eddy currents or AC loss. So here we can just use, or in the winding itself, there's only the DC component existing in the winding. For the simulation, I use just one small part of the lamination stack. So the length of the stack is 10 millimeters. So basically, this is a typical dimension of a segmented magnet inside the rotor. That's why I've chosen these 10 millimeters of stack length. And if you would want to consider, let's say, a real machine, then let's say the machine would be 10 times or 12 times longer than this model. So this model consists only of one segmented magnet in axial direction, and therefore we want to evaluate the eddy current loss. And the idea of the investigation is, in the end, to use these models and investigate in the results of all the 4 approaches we have seen on the slide before. Now, I want to give some insight into the analytical equations I've used for this comparison. And let's say these analytical equations are needed to assess the results of the 2D simulation and recalculate the results to a 3D value. And the basis of this segmentation factor or 2D to 3D factor is this publication from Dr. Gerling from the University of Munich. And the basic idea is as follows. So here we see the model of a magnet. So, and the dimensions of the magnet are represented with this full line. And the idea is now that the eddy current inside the magnet will flow along the path of this dashed line. And this path is exactly in the middle between the outer dimension and the center of the magnet. And this gives a length and a path for the current, and this model also gives a cross-section for the eddy current. And this way, one can calculate, based on this model, let's say a virtual resistance of the magnet with the given dimensions. So it's not a real, it's just a virtual value, because the eddy current will flow not exactly on this path, but it gives some relation of the resistance of the magnet, or of the resistance which the eddy current faces. And the idea is now, if we want to consider segmentation, if we now split this magnet model into two parts. So one part would be from the top side to the center of this magnet model, and the second part would go from the bottom to the center of this model. And then in each magnet, again, each magnet would have a new center, and in each magnet would flow an eddy current again, which is also again calculated in the same way as the resistance, or where the resistance is calculated in the same way as for the unsegmented magnet model. And for the segmented model, we see this equation, so it's basically the same, but now we have here the number of segmentations included. So NB represents the number of segments in the B direction, and NL represents the number of segments in the length direction, so usually the axial direction. And now if you want to calculate the reduction factor, if you go from the unsegmented resistance to the segmented resistance, we just put these two values in relation and multiply it with the number of magnets we have in the end. And in this case, for this dimension, we get a reduction factor of 4.2. Maybe just to answer before the question arises, well, because we do not have a real in this simulation, or in this example, I do not deal with the segmentation, but I use this approach to recalculate the results from a 2D simulation to 3D result values, or to 3D losses. And in the end, the idea is, if you have a 2D simulation, the upper path and the lower path of the current, eddy current, is not existing, or is very small compared to the actual component. As we have seen in 2 slides before, so in a 2D simulation, we can only consider a current density in the actual component. So let's say here in the length of L. And if you think of a 2D simulation, you would make this magnet endlessly long, then this component in the B direction becomes very small. And that's the idea of how to calculate this reduction factor for a 2D simulation to a 3D simulation. So it's just to make this L very big and to divide this length into many parts, so that in the end, the segmented dimension of L would be the length you have really in the real E-motor model. Let's say, to make this direction in Z very long, we multiply this real existing length of 10 millimeters with 1,000. So we get, let's say, 10,000 millimeters. And afterwards, for the segmented model, we divide this 10,000 millimeters long magnet into 1,000 segmented, or into 1,000 segments. And that's the approach how one can calculate the 2D FEA results to a 3D value of the eddy current loss. And that's in the end the factor I will always use for the recalculation of the FEA simulated 2D losses. As said, so this approach bases mainly on the ohmic component of the losses. So if you divide this value, or if you use this value to divide the FEA simulated losses, then you suppose that the frequency components inside the eddy current loss is quite low. And to check, or to have some kind of approach to say, okay, this is low frequency, this is high frequency, we can use the so-called skin depth calculation. I think this is known from conductors, where the current distribution in the round wire is calculated, and in the skin depth, a big portion of the current is flowing inside a conductor. And you can also use this skin depth calculation for the magnet. For copper, you can see it here in the diagram. If you increase the frequency, the skin depth reduces to a very low value. And the same you can do with the magnet material. It gives the same straight line in the logarithmic diagram. And for a frequency of 10,000 Hertz, you get a skin depth of about 6.5 millimeters. And this is already in the range of the dimensions of the magnet. Now, if you consider this 18 millimeters of width of the magnet, we are already inside inside a dimension where we have to consider the skin depth, and where we have to consider that the current, that the eddy current is not only limited by the ohmic component of the magnet, but also by the inductive component of the magnet. And because the eddy current is not only limited by the ohmic component, but also by the inductive component. This means if we increase virtually the resistance by segmentation of the magnet, we increase the resistance, but we do not increase the inductance in the same way. So the inductance, or the inductive component of the resistance, remain the same. And this way, the eddy current does not decrease, but now for high frequency, the eddy current has to pass a higher resistance. And this way, for high frequency, the segmentation do not lead to a reduction of losses, but it can even lead to an increase of losses for high frequency eddy current components. So, and this is because of the limitation of this eddy current by ohmic component and an inductive component. And in the end, to evaluate if this is the case for the e-motor design and for the operating point of interest, you can use the skin depth. Now let's come to the example.
Stefan, can I display the poll just before, which was related to your slide? So yes, we would like just to have your input on this question. Which simulation method do you find most reliable for predicting eddy current losses in magnets? So I'll let you just a few minutes. You have several proposals. We will close in 20 seconds. Okay, thank you. The main answers, Stefan, 3D simulations for 67% of the people.
Okay, sounds good. Probably it also depends on what is the stage of design of e-motor. I think for an initial stage, it will be a bit more in 2D. For final simulations, I think one will focus a bit more on 3D simulation. So I think it also depends on the where you are in the design process of the e-motor. Okay. Okay, let's come back to the to the example. As described, my e-motor model, I want to supply with a specific current and to supply it with a reasonable current. I created such kinds of operation maps for this e-motor model, and goal was now to simulate at 30 Newton meters of torque and 3000 RPM. And this gives, according to this operating maps, a certain current in the d-axis and a certain current in the q-axis. Or in the end, I fed this current amplitude and this with this angle to the e-motor. And these graphs were created with the efficiency study in JMAC, so it was quite easy to extract these currents or this current and angle from the simulation results. And now I would like to investigate this operating point with these 4 approaches. Here again we see the model, the meshed model I have used. So just to shortly explain, so the 2D model has roughly 9,000 mesh elements, and for this simulation with the sinusoidal current, I simulated one electrical period and splitted this period into 144 steps with the simulation on one core. And duration was roughly 6 seconds for this simulation. For the simulation with the PWM current, with the 2D model, I used 2,500 steps for one electrical period. And also simulation on one core. And the simulation took roughly a bit more than 1 minute. The 3D model has a bit some more mesh elements, but I think 130,000 mesh elements is still not not a big model. It's let's say mid-sized and can be well calculated on a workstation. And for the sinusoidal current with the same parameters as for the 2D model, it took roughly 21 minutes for the simulation. For the PWM case, I used 8 cores on the workstation, and simulation took roughly 3 hours for this one operating point. So I think this is all reasonable, and I think most of you can do this on the workstation quite well, and this is not a simulation that is too far to do. And now let's come to the results. Here's just as an overview, the torque results of the 2D models here in red and black, and the results of the 3D model. And in the 3D, the torque is slightly lower compared to the 2D results because of the actual stray flux of my model. But this has only a small influence on the eddy current loss in the magnet. So it's just for information. So in the 3D model, we have some small actual stray flux, which also reduces the average torque. And now let's come to the eddy current loss with sinusoidal current supply. Now we can see a table with in each column we can find the approaches defined. So approach 4 again, it's the 3D, the result of the 3D model. And this gives roughly 0.7 watt as a reference. Please don't forget, so it's a very small number, but we have to multiply it with the length of the machine and the periodicity of the motor. So this is just a value of a small part of the motor. So, and if you now compare the other 3 approaches dealing with the 2D simulation, the first one, where we do not consider any segmentation factor or 2D, 3D factor, we have very high losses compared to the 3D results, because in this 2D simulation, we fully miss the resistivity in the XY plane of the magnet. And this way, the eddy current is simulated to be too big, and according to this, the results are too big afterwards. Now we can also see it in the contour plot of the current density. So the current density is far higher than in the approach 3 or far higher than in the 3D model. So, and this is because the current density is not really limited with the correct resistance of the magnet. Approach 2, where we apply the segmentation factor to the losses, provides relatively good results, but it's too low compared to the reference. So it probably means that there are already some higher frequency loss components which are not considered with this approach. And approach 3 is, let's say, from the 2D variance, the one which is closest to the reference. And this is probably because the resistivity of the material is adapted according to the dimensions of the magnet, of the 3D dimensions of the magnet. And this way, it, on the one hand side, reduces the eddy current density in the magnet. But on the other hand side, the resistivity is increased and it creates losses which are quite close to the 3D variant, but still lower than the 3D variant, because it cannot fully represent the correct current path as it can be represented in 3D. And now let's come to the results with the PWM current. Just for information, so here we have the torque again of the in black and red of the 2D models, and in green for the 3D. It's again the 3D model provides a smaller torque compared to the 2D models due to the same reason as for the sinusoidal current supply. And here on the right lower side, we see the PWM current I fed to these models. And we can see the typical PWM ripple in this current, but we can also see some additional harmonics due to the control, which has created this PWM current. So, and these harmonics will also create some additional joule loss in the magnets. And how did I create this PWM current, or how was the approach? So I used the 2D models with an inverter model, which already exists as a macro inside JMAC. And I used the field-oriented control. Also, everything is inside JMAC. And with this approach, I created a PWM current. And afterwards, I fed this PWM current to all models, so to the 2D models and the 3D models, just to be sure that this PWM current and the boundary conditions for all models are as similar as possible for the PWM case. And now let's have a look to the results. With the PWM current, maybe let's start again with the 3D results of the 3D model. Maybe you remember, so for the sinusoidal current supply, we had a value of 0.7 watt. Now with the PWM, we have 17 watt per, for this simulated part of the e-motor. So it's roughly 25 times the value of the sinusoidal current supply. But please do not use this relation. So this 25 times, this is not a, let's say, constant relation for all operating points. This is really a relation valid for this operating point I've chosen. So it can be different for other operating points. But for this operating point, it's a quite big difference. And here, approach 3, here we have the approach where we apply the segmentation factor to the resistivity or conductivity of the material, and we get an even higher value. We overestimate the eddy current loss in the magnets with the 2D model, but it's quite close to the 3D model. So it's an error of, let's say, 40% or something like this. So this is quite close compared to the value we get with approach 2. Here we have, so in approach 2, we have divided the joule losses we get as a result from the 2D simulation, and we have divided this value with the segmentation factor. And this gives a far too low value for the eddy current loss. And this is mainly because for the PWM case, we have lots of eddy current components with high frequency. And this cannot be represented well with this approach 2. Because of this inductive and ohmic components, which are limiting the eddy current of the magnet. And let's say by chance, or I think by coincidence, the approach 1 provides a very similar result as approach 3. For me, this is just coincidence because boundary conditions are completely different between approach 1 and approach 3. So that's why I think this is only coincidence that these values are the same. So I wouldn't, let's say, generalize it for the whole operation map. So it needs to be verified afterwards. But this is something I would say this is not, would not be, or I couldn't explain if this would be a real physical relation. So I think this is just coincidence that these values are the same. Then as a summary, so I would also here approach 3 shows to have the most accurate results for the 2D simulation compared to the 3D simulation. Now let's summarize what we have seen on the previous slides. So 3D provides most accurate results because it can represent the best the current distribution inside the magnets. And but 2D simulation, especially if you consider a good segmentation factor or a good factor to recalculate the results from the 2D simulation to the 3D simulation. And then 2D simulation can provide a good first guess for the losses inside the magnets. But as you already do, or as already most of you do, at least as a final simulation, it's really recommended to do 3D simulation to take into account the eddy current loss of the magnets. For the 2D approaches, I think approach 3 proves to be the best approach to consider the eddy current loss magnets for all supplies, so for sinusoidal current supply and for PWM current supply. And if you compare sinusoidal to PWM current, we can see a strong increase of the eddy current loss in the magnets. So as far as I know, so the first simulations that are done for an e-motor design are usually fed with sinusoidal current. But I think, as soon as possible, one should really consider simulation with PWM current to really assess the characteristics of the e-motor, especially regarding thermal design. And if you start to think about the cooling concept, then really start to do simulation with PWM. And now some words about the mesh quality and the number of time steps. For the mesh quality, here is what I've used for this simulation. I've used 10 elements in the actual direction for the magnets, and a similarly fine distribution of mesh elements in the XY plane. And to assess what should be the a good size of the mesh elements, you can also use the skin depth. If you consider 1/5 of the skin depth, I think if you consider PWM and harmonics of PWM, you end up with very small elements, or you can end up with very small elements in the magnet. And and this can also explain why, if you increase the number of mesh elements, then you can better represent the current distribution inside the magnet, and the results will become also more accurate if you distribute more mesh elements inside the magnets. And regarding time step, here on the top, I've added an exemplary picture of the joule losses in one magnet over time for the PWM supply. And this is mainly to show the influence of the time step and what is the result afterwards for the joule loss in one magnet. And here you can see with a very rough time step, this rough time step cannot represent all the harmonics which exists inside the PWM. So you will end up with a very low value of eddy current loss in magnets. And if you then increase the number of steps per period, or if you decrease the time step, then results become more accurate. And a medium result, let's say, is the blue line. And then if you refine this further to the green variant, then you get even better results. And further simulation have shown, so if you further increase, or if you further reduce the time step, then there are still some minor improvements in the curve of the joule loss curve, so that there are some more joule loss considered if you further decrease the time step. So that is what I want to recommend. So you can use the frequency which you want to consider in this loss calculation to determine the time step of the simulation. And you can also use the frequency, the maximum frequency, to determine the size of the elements, of the mesh elements inside the magnets, and maybe also in the surrounding parts of the e-motor, to have a good mesh afterwards. And yeah, that's my proposal and my recommendation to do this when you want to accurately simulate the eddy currents in the magnets. And I think that's it from my side. And hope you enjoyed the presentation and can take some informations from it. And I'm looking forward for your questions.
Thank you, Stefan. I think we have some. I will let Bernd maybe help you on or guide you on this one.
I have answered some questions, but there are still a few. I don't know which ones were valid because some of the questions have been raised early and you answered them later. But maybe you can go through some questions and answer them now. Some like the PWM switching frequency, which frequency has been used in the simulation?
So it was 10 kilohertz. Let's say a very conventional value.
And there was a question about the used operating point for the simulation.
A specific question. So
which operating point did you use for the simulation?
It's the, let's say, the 3000 RPM, 30 Newton meter operating point. And it was chosen a bit because for the PWM, it's very important what the value of the modulation factor is. And here in this area, we have a quite big modulation factor, but it's not the modulation factor is not 1. It's, let's say, 0.8. Usually, current ripple due to PWM is biggest if you have something around a modulation factor of something around 0.5. Here it was a bit, maybe 0.8 modulation factor. But that was a small importance for me, so that we have not a modulation factor of 1, but just a reasonable modulation factor for the operating point.
And another question from Matthias Lindner. He were asking about comparison between extruded mesh and auto mesh regarding differences in eddy current in 3D.
Good question. So this is something that has to be done. Usually, so if we consider extruded mesh, so in 2D we have, or if you use the auto mesh, we have always tetrahedral elements. And if you use extruded mesh, we have, at least in the axial direction, more quadrilateral elements. And the, let's say, the coupling in the axial direction is probably not as good as if you use tetrahedral elements. So maybe it could even be, if you use tetrahedral elements also in the axial direction, then it might provide some improvements regarding accuracy, but on the cost of more mesh elements.
Maybe you can go through the questions on your side because I don't want to read them, Mary. There was a question for a 3D model, if the model is surrounded by air actually, or if you have a natural boundary condition applied. I think it has been surrounded by air.
It depends on which edge. So this was not described in the model. That's right.
Axial direction. So.
An axial. It was an axial direction. I've applied the symmetry boundary. So in JMX, symmetry boundary means that the current can flow in a rectangular direction to the symmetry boundary, and all flux densities go in parallel to the symmetry boundary. And to allow to feed in current into the windings, I have to apply the symmetry boundary to allow current to flow into the model.
Yeah.
Sure.
And there was a question if you have tried other PWM frequencies like 100 kilohertz. I think it's not used in EVs. Nobody uses 100 kilohertz in a real inverter, not even on silicon carbide, because the losses would be too high. But generally, did you compare using other PWM frequencies?
Not in this case. Yeah, I think this could be. Maybe the question comes from a participant who is not involved in the drivetrain simulation of vehicles. So maybe it's another application.
It's for charging. The question was for charging mainly,
okay,
because
yeah.
there you have this frequency.
Yeah.
Inductor.
Okay. No, I haven't used such high frequencies. Maybe for traction drives, 20 kilohertz could be reasonable. But no, in this case, for this exemplary investigation, I've only used the 10 kilohertz. But at least in the range of 20 kilohertz or 5 kilohertz, I wouldn't expect much change regarding the relation between the results. So it will give similar results, maybe on another level, but the relation should be similar.
And there was a very interesting question that I actually had on my own as well. So the segmentation we have discussed was actually, but there is also circumferential segmentation like on Tesla existing, like the cutted and re-glued magnets. So how does this segmentation compare regarding 2D analytical, 2D FEA and 3D?
Yeah, basically in the circumferential segmentation, you can simulate in a 2D model better than the actual segmentation. But from the principle, the effect should be similar as for the actual segmentation in the end. The same approaches apply. You can also, if you do the segmentation in circumferential direction, you can recalculate the 2D results to a 3D loss value afterwards, also for circumferential segmentation. The same approach applies. And the only thing is that you can, let's say, create some relation between non-segmented magnet and segmented magnet in a 2D simulation better than you can do it for an actual segmentation with 2D simulation.
And there was another question for the 3D model. If the 3D model is only as long as one magnet segment, wouldn't it make more sense to set zero flux boundary condition at the front and face of the model, such as the torque, then also matches the 2D calculation? I don't really understand the question, but it's about the boundary condition, I suppose.
Yeah, so I think if you simulate a full machine, then yeah, maybe there could be some differences because on, let's say, the magnet in the front has its eddy current and the next magnet will have its eddy current. And on the face where the two magnets are close together, you have one current flowing in one direction and the eddy current of the other magnet is flowing in the opposite direction and maybe annihilate each other a bit. Could be, so they can influence each other. This can be considered in a bigger model, that's correct. And could also, let's say, provide different total loss values compared to my example model with this only one slice or one segment of magnet. But let's say in relation, or the let's say the overall outcome of this approach would still be valid, I think.
And there was a question or just a comment maybe that the proposed methods work mainly in straight configuration. That means extruded configuration.
Yeah.
If in case you have really a skewed magnet or a skewed conductor, the question or just a comment was that this cannot be applied because the inaccuracy of this tilted geometry is of course not so easily be solved by this analytical approach.
That's correct. Or if you think of, let's say, somehow shaped magnets, so maybe then you can create an own segmentation factor based on the approach presented. But yeah, you are correct. It's for, let's say, magnets with special shapes, it's more difficult to create such kind of analytical factor. But in the end, you always have the 3D simulation available, and you can calculate the results.
I mean, the answer was given at the beginning already. If 70% of you is agreeing that using 3D is probably the better approach, this answers the question. In case you have any specialties in the magnet, let's say different conductivity regions, which also exists. You know, we have magnets where you have grain diffusion boundary, where the boundary has a different dysprosium content as the middle layer, and this touches the conductivity as well, and also other methods. This, of course, cannot be solved by any analytical approach. It's too inaccurate. And there was a question about the meshing of JMAC 3D. Maybe I can answer this. JMAC provides many different meshing methods. There's automatic meshing in 3D as well. Stefan has used the automatic extruded mesh. So you have an extrusion direction, which you can also manually adjust if you want. But there are much more meshing conditions in 3D that you might apply regarding the faces, certain points or lines where you can have a finer mesh. So this is a bit out of scope of this webinar, but yes, there are many mesh conditions that can be applied. So you don't have to do a full manual mesh. And there was a question about surface magnets. Can I use the same approach methods? I don't think there is any contradiction. So in my opinion, you can also use it for surface magnets.
I would also think so, yes. It's a similar approach. Except for the form factor, maybe. But in principle, it should be feasible, yeah.
There was a comment, aside from the simulation, are you aware of any sound test method that can measure the losses of permanent magnet? So far, we are dealing here only with simulation. So we are a company which does no testing. But since Stefan and me both have long time experience also on testing of those things, and I myself has done a master thesis on this in the past, I know that there are methods of using the time constant of the eddy current in the magnet and try to measure this from the stator or with some additional coils in the air gap. But I've never heard of any sound test method. So if you can provide some information to us, that would be quite interesting. So it's basically all of the questions, I think. The rest is just comments. So Stefan, if there is no comment from your side, I think we can conclude here if there are not any more questions.
Yeah, from my side, I think that's all. Again, I want to thank you for the nice discussion and for the nice questions. And yeah.
Okay.
But there's no further comment from my side.
Bernd, on your side, is it okay as well?
Okay, yeah. Thank you, Stefan, again for the interesting presentation. I think that's a topic that is really of interest of many e-motor designers, and it's still a very important topic because magnets are quite costly, and we're trying to use cheaper magnets which are not so capable in high temperature region. And also it has some environmental issues, especially the heavy rare earth materials in the magnets. So that's really getting more and more important. Thank you, Stefan.
Thank you, Stefan. Thank you, Bernd. Thank you to all of you for attending. As mentioned, the presentation and the recording will be shared shortly. You should receive them by email. And we wish you all a good evening. Bye. Thank you.
Thank you. Bye.
You, goodbye.